Good evening to all. Is it visible? Full screen, na? Okay, okay. So let's start. So good evening to all of you. This is NPTEL course characterization of polymers, elastomers and composites, week 7, already taught by Professor Santanu Chattopadhyay. And here I am Somresh Ghosh as a teaching assistant for clearing your doubts. So we are discussing about different spectroscopical technique characterize polymers. We have discussed UVVs, we have discussed FTIR, we have also discussed Raman, and today we will discuss a very interesting and very important spectroscopy technique, that is nuclear magnetic resonance spectroscopy. The importance of NMR, because it can precisely determine the structure any organic molecule. From FTIR, from UV, we analyze different presence of functional group. Also we have analyzed structurally, but we cannot uh, very precisely say from FTIR or UV that this is the structure of my molecule. For that, you must perform or you must go for NMR spectroscopy. Now, the name of the spectroscopy, that is nuclear magnetic resonance, it says that there is a nuclear spin, basically nuclear spin. That's why it is nuclear is associated with this spectroscopy. And also there is another term, that is magnetic. That means there is the presence of magnetic field and nuclear spin. So these two terms are very much important, and we'll discuss how this nuclear spin and magnetic field actually works to determine the structure. So for the first 50 years, NMR only referred as NMR, that is nuclear magnetic spectroscopy. That is the eminent technique for determining structure of organic compound. Of all the spectroscopic method, it is the only one for which a complete analysis and interpretation of the entire spectrum is normally expected. Although larger amount of sample are needed as compared to your mass spectroscopy, you need very small amount in mass spectroscopy. Though in case of NMR, it is not too much large. Max to max, you may need around 8 to 10 mg to do NMR analysis. But still, it is little bit larger as compared to mass. But the advantage is it is non-destructive analysis. After doing the test, you can take the sample and you can do other physical testing. Now, the nuclei of many elemental isotopes have a characteristic spin. So we have already discussed the electronic spin. Now there is also nuclear spin. Now some nuclei have integral spin. For example, if I, that is nuclear spin, equal to 1 to 3, some have fractional spin. I will discuss why, when it will be integral and when it will be fractional spin. And some of nuclei also have a spin 0, where the number of electron or proton, that is paired. It is even number of proton or even number of neutron. For example, 12C, 16 oxygen, all have paired number of or even number of proton and neutron. These elements will have no spin, magnetically no spin. So isotopes of particular interest and used to organic chemist, basically 1H, that is proton, 13C, that is the isotope of carbon 13, 19 fluorine and 31 phosphorus, all of which have half integral. Since you see there is unpaired or uneven number of proton is there. There is one, here is also one unpaired proton. In case of 19F, it is also one unpaired proton, and in case of 31P, this is also one unpaired proton. Since the analysis of this spin state is fairly straightforward, so our discussion will be limited to this and other I equal to half nuclei. Now from where this half is coming? Now we know that any spinning charge that will generate magnetic field, as well as of course it has, because of charge it has also electric field also. When a charge species is moving or spinning, it will generate magnetic field. Now the resultant spin magnetic or the magnetic field have a specific magnetic moment, and that is proportional to the spin. Now in presence of external field, so if a charge species is moving, so it will generate some magnetic field, and that magnetic field has a specific direction. Now if there is external magnetic field is present, for example if it is B0, now that charge species will have two spin states. One is plus half, another one is minus half. Now when it is plus half, when it is minus half, when the direction of B0 and the direction of magnetic moment that is generated by the species is in the same direction or it is aligned, that will be termed as plus half or alpha. And if the species resultant magnetic moment has opposite direction, that is inverse direction, then it will be termed as a minus half or beta. Now that depends on the direction of the spin. For example, it is swing this direction, so B0, the magnetic moment is acting from towards B0, the same direction with B0. In case of here, it is inverse direction or opposite direction to B0. Based on this, we will differentiate two spin state. One is the plus half and one is minus half. And the plus half will have a lower energy, and the minus half spin state that is opposing to the external magnetic field direction will represent the higher energy state. The magnetic moment that is equivalent to gamma I h, which is the Planck's constant, divided by twice pi. Now very small number of nuclei, for example 1H, 13C, 19F and 31P have a it's unpaired proton, and those have a two different spin state. 1 minute. Now a spinning charge create magnetic moment, as I say, and that spinning charge we can assume as a tiny magnet. When it is charge species is spinning, since it is generating magnetic field, we can assume that species as a very small magnet. Now if we place that nuclei in a magnetic field, they can line up or against the field by spinning clockwise or anti-clockwise direction. So if it is clockwise, that is favorable to the magnetic field and it is lower energy, that is called alpha. If it is opposing the external magnetic field, that is unfavorable, it will have a higher energy state. In that way, two splitting are possible. Now how much splitting will takes place, that depends on the strength of the external magnetic field. For example, if you are applying 60 or 10 5 Tesla, and if you apply 10 Tesla, so obviously based on the magnetic field strength, external magnetic field strength, the splitting will be different. That means the gap between the excited state and ground state will higher in case of higher magnetic field. Okay, now note the nuclei that don't have spin, for example 12C, that is usually maximum carbon allotrope is 12. There is no difference in energy alignments in presence of magnetic field because it is not generating magnetic moment, as there is no unpaired electron. So when there will be unpaired electron, so there must be unpaired proton, and then that will generate the magnetic moment If all proton or electron are paired up, it will not generate any magnetic field. That's why if it is present or if magnetic field is there, it will not split that 12C or 16 oxygen, etc. So we cannot do NMR spectroscopy on 12C or 16 oxygen or uh, deuterium because of as they are not magnetically positive, or they cannot generate magnetic field by their own. Now spin active nuclei that must behave as a tiny magnet, and the angular momentum, since it is rotating around the nucleus, so it will not be equal to 0. First condition is I should not be 0, and for that you must have a odd number of neutron or odd number of proton, or both odd number of proton and odd number of neutron. So first is either odd number of proton or odd number of neutron, or both odd number of proton and odd number of neutron. So those elements will be NMR active. For example, a spinning nucleus, for example, a proton behaves as a spinning charge and generate a magnetic field. Now that resulting spin magnet has a magnetic moment that is proportional to the spin, and that will be expressed as omega equal to twice pi mu. That is the angular frequency. Now spin quantum number, why it is 0, why it is half, that depends on the number of unpaired electron or proton. In case of 1H, 13C, already I have told, both have single unpaired electron proton, that's why it is half. So basically that is uh, S into S plus 1. If you do that equation, it will S is the number of unpaired electron, you will get the spin quantum number. Now according to Planck's law, delta E equal to h nu we know, where h is the Planck's constant and nu is the frequency of electromagnetic radiation. As a charge species having a charge, it will generate electric field, and because of it is moving, it will also generate magnetic field. That's why it will generate electromagnetic radiation. Now again, the radio frequency can provide the energy difference necessary for the nuclear spin to shift states. That is, delta E very proportional to B0, and delta E equal to h nu. So h nu proportional to B0. So obviously nu proportional to B0. Therefore, the frequency of resonance mu is directly proportional to the strength of the external magnetic field. The proportionality constant equal to gamma by twice pi. This is the intrinsic property, gyromagnetic ratio of the nucleus. So for each and every element, the gyromagnetic ratio will be different. The constant is just a measure of how strong nuclear magnetic field is. So obviously, if B0 is high, your V will be high. Now this gamma or nu is called the Larmor frequency, and different spin active nuclei will have different Larmor frequency. We will discuss what is the Larmor frequency. Now when a spinning nucleus is spinning, so it is not at a 0 degree angle, it is spinning by at a specific angle. The motion is like this. In that way, a nucleus is spinning. Now it is represented as E equal to minus mu b cos theta, where theta is the angle between the direction of the applied field and axis of nuclear rotation. So this rotational frequency is called the Larmor frequency, and when a spinning charge is spinning in presence of external magnetic field, it is spinning at a specific angle in between the direction of applied field and the axis of the nuclear spin. Now if the energy is absorbed by the nucleus, then the angle of precession of theta will change. For a nuclear spin half, absorption of radiation flips the magnetic moment so that it opposes the applied field to the higher energy state. So V equal to gamma B0 by 2 pi. Now from here, where what we are actually doing in case of NMR. First, in presence of magnetic field, there is a splitting of the nucleus energy state. So in that way it is splitted. Now we know, according to Planck's law, delta E, the gap between the excited state and ground state is h nu. Now, that same amount of energy we will provide through radio frequency, and that way it will resonate. So this h nu, or the energy gap between the two, will be equivalent to the external radio frequency radiation. In that way we will excite this ground state to this excited state. So first you split in two state by providing external magnetic field. Then you match the energy gap by providing radio frequency. So this is the basic of NMR. Now depending on the splitting, or depending on the, yes, ma'am, it is not electron. Ma'am, it is not electron. It is not electron. It is the proton. This proton, because it is nuclear spin. So in nucleus there is neutron and proton. Okay, so there is neutron and proton. So that's why when there is a unpaired electron means obviously there is unpaired proton, because we know the number of proton equivalent to number of electron. Now when there is unpaired electron, so there is unpaired proton also, the same number of unpaired proton. So only unpaired electron or unpaired proton will generate the magnetic moment. Okay, so that's why 1H13C isotope is only NMR active, because they can generate magnetic moment. Now what we are doing in NMR, those are magnetically positive, that means they can generate magnetic moment. So in presence of external field, because of the, we know there is two different spin quantum number, plus up and minus up, based on the direction of the magnetic moment that is generating. So that will be splitted, and that splitting gap will be different for strength, based on strength of the external magnetic field. For example, if it is 1.4 Tesla, the gap is low. When it is 2.35, the gap is higher. Now when the already splitting has been done in presence of external magnetic field, then you resonate the gap by providing the radio frequency to excite that ground state 1 to excited state 1. Yes, now please ask. Resonating, what does resonating means here? Resonance means matching. That is I want to mean. Resonance means I am matching that gap by providing energy through radio frequency, because the gap what is generating in case of NMR, because of the external magnetic field, that is, it becomes equivalent to the energy of the radio frequency of electromagnetic different electromagnetic radiation. So we know there are different electromagnetic radiation, we have discussed as a very first class. So in case of radio frequency, it has a very high wavelength, and that energy, because we know delta equal to h nu, so that amount of energy is actually matched with the splitted proton in NMR. So that's why I am saying we will resonate that energy gap by providing radio frequency. If you provide IR, that will be higher energy, so it cannot match. So we know from quantum, say only whenever it will exactly match, that will be as absorbed, or that will be emit. If you provide higher, so it will not absorb, it will pass through. The gap, the energy what it is generating, that is matching only with your radio frequency energy. That's why you need radio frequency. Yes sir, Nair sir, you are asking something? Yes. Proton. Yes, hydrogen nucleus. Yes, hydrogen nucleus. huh, 1.4 Celsius, and that is the external magnetic field. If you, huh, yes, electromagnetic radiations are what? First of all, just listen. First of all, whenever there is a unpaired electron or unpaired proton, that species will generate magnetic moment. It has that inherent property, it can generate magnetic moment. That's why proton 13C, 17 oxygen and 31P can generate magnetic moment. Okay. Now when it has its own magnetic moment, now when you again apply external magnetic field, now there is will interaction. Based on that, it will be splitted. How it will split? Because that unpaired electron, so let's say there is a 1 lakh proton atom. Okay. Now when there is a external magnetic field, so obviously all 1 lakh proton 1 lakh proton will not be rotating in the same direction. There must be some opposite direction also. That is the probability, na? It should not be 100 and 0. Now based on the its spinning direction, so the assumption is if it is aligned with the direction of external magnetic field, because we know magnetic field is vector quantity. Now if it is aligned with the direction of the external magnetic field, that will be the lowest energy, because now it is stable. But when those proton, those are spinning in opposite direction and their magnetic moment is directing in the opposite direction towards the magnetic field, so that will be the higher energy. Now depending on the strength of the external magnetic field, the gap between these two states, what we have called it a ground state or excited state, the energy gap or the distance between these two will different based on the external magnetic field. If it is higher, so obviously the gap will be high. Okay. It is case of a magnetic field. Yes. 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 It is also electromagnetic radiation. Okay. Now, now when we have splitted this state, two state, now if I want to resonate means what? We know in quantum, when the energy is exactly matching, then only it will can absorb. Unless, until and unless it is not matching, it will not absorb. For example, what we have studied in FTI, if you provide for example X-ray, the vibrational frequency or rotational frequency what the energy is generating, it is not matching with your X-ray, so that's why it will not interact until and unless it is purely matching. That is actually resonating. That term I am asking, that matching is equivalent to resonating, flipping, or whatever you can say. Yes. Yes. Huh. It will flip. It will flip. Exactly. Yes. But because all are covering radio frequency, but now you just see that it is not 60, now it is become 100, because now energy gap is also increased na, because of higher magnetic field. Yes, that radio frequency, wherever it is a 7 Tesla, still the radio frequency can match. But if you provide IR, it will not match, because IR has a higher energy. So what is the energy difference is getting here or generating here? It is it is covered by the radio frequency only. You cannot provide IR or something else, that will not enter or that will not flip that spin. Yes sir, yes sir, you ask. Yes. 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 Exactly. Exact. Yes. Is in NMR in NMR you actually you start from 7 Tesla, or right now those NMR, I mean very sophisticated lab, they have even 60 megahertz, 900 megahertz NMR. So in that case, it may be 12 Tesla or 16 Tesla, and that's why NMR machine is that much cost, almost 10 to 12 crore. So you provide that high amount of magnetic field until unless that much, because that magnetic moment, because of that spinning species, that is very much low, na, because that is very small, that is very small. The magnetic moment generating by that proton, that is very small. That's why you need very high magnetic field, so that the differentiate will be a large, otherwise it will merge with other element or with other I mean, we will discuss what coupling will takes place. Until unless it is very high, so those peaks will be merged, you cannot get a hyperfine structure. For that you need to provide higher magnetic field, then you will get very precisely data. Even if from polymer also you can get. For that we need to do a very high scan also, we will discuss in later slide. So till now it is clear now what is the basic of the NMR. So first, it will generate magnetic moment, only those element will be studied by NMR. So you cannot study 12C through NMR because it will not generate any magnetic moment. So first you have to select those whose nuclei will be electromagnetically active, then you split the nuclear spin by presence of magnetic field. After that splitting, you resonate by providing radio frequency, and you will get the data. Now, Boltzmann distribution, what we have discussed about the flipping. So always the ground state will have a higher population, and that follow the equation n minus by n plus, that is the excited state, and this is the ground state population, will be equivalent to the e to the power minus delta E activation energy by kT. K is the Boltzmann's constant. Now the signal is thus proportional to the population difference between the states, and this is very necessary condition that that must be the population density in ground state must be higher as compared to your excited state. So in that case you must also uh, say that what will be the significance of temperature, and the signal is thus proportional to the population difference between the states. So here you see the after the splitting, so three protons are in excited state and 6 or 7, so they are the ground state always should be more populated as compared to your excited state. So here it is what we are discussing, that radio frequency, that is the least energy, that has the least energy if you compare with all others electromagnetic radiation. So in radio frequency actually covering the in used in the NMR spectroscopy. Now imagine, for example, if we place a CH4, that is methane, in magnetic field, we can probe the energy difference of alpha and beta state of the protons, not carbon, of the protons, by irradiating with the electromagnetic radiation just the exact or same amount of energy. Now if a magnet of 7.05 Tesla, it takes the radiation to about 300 megahertz radio waves. So if we bombard the molecule with 300 megahertz radio waves, the protons will absorb that much of energy, and we can measure that absorbance. Now if a magnet of 11.75 Tesla, it will equivalent to the radio frequency with 500 megahertz, and it will generate greater difference between these two states. So see here it is clearly visible, if it is 300, the gap is this, if it is 500, the gap will be this. Now the problem is, if for example one lab in Bombay and one lab in Chennai, they want to compare the data using the magnetic of different states. Someone is using 5 Tesla, someone is using 7 Tesla. So that will create problem, because you will get data from the NMR at different data you will get. So that's why the international standard is you will provide the NMR data, 1H NMR data, by using the term chemical shift. Okay, we will discuss what is chemical shift. Now here another two important term, one is shielding, one is deshielding. So what we have learned till now, that because of nuclear spin we are getting the NMR data and it is generating magnetic moment. Now there obviously the nuclear, if it is in various electronic environment, so there will be the different magnetic moment will generate and different amount of energy required to bring them to resonate. So here for example there is one H proton, one is directing in from lower, if we say that it is deshielded. Deshielded means what? So electrons are also moving around the nucleus. Now there is a presence of external magnetic field. Okay. So obviously when electrons, the number of electrons around the nucleus will be higher, so there will be the more chance of opposing that external magnetic field. Higher will be the number, higher will be the probability to oppose the external magnetic field. And when the electron density around the nucleus will be lower, so the probability of opposing the external magnetic field will be lower. In that way it is called that shielding, that means shielding that or opposing the external magnetic field. Deshielding means it is less opposing the external magnetic field, or other way you may say the deshielded nucleus is actually feeling more magnetic strength or external magnetic field strength as compared to the shielded one. So what we will say, that higher the electron density, the shielding will be higher, that nucleus will feel low or less amount of external magnetic field strength, and the deshielded nucleus will feel higher or more external magnetic field strength. So energy required for spin active nuclei to go from alpha to beta state or ground state to excited will be greater for the deshielded one as compared to shielded one. Is it clear what is shielding and deshielding and why the energy required is higher in case of deshielded one as compared to a shielded one? Clear na? Okay. Now what is chemical shift? Chemical shift is a function of nucleus and its environment. So it is difficult to measure the absolute frequency in NMR, but it is much easier experimentally to measure very precise frequency differences between the resonances. And chemical shift is defined as the resonant frequency relative to a standard one. So what we do actually when we do NMR analysis, first you do your standard sample. So first run the standard sample. After that, with the same standard, you are doing the your sample, and then the difference between the standard and your sample is actually you are representing. So chemical shift is defined as the resonant frequency relative to the standard in applied magnetic field, and it is measured relative to a reference compound. For 1H NMR and 13 cm NMR, the general reference that is used is the trimethylsilane. So this is the standard sample that is used in NMR, that is tetramethylsilane, and as compared to tetramethylsilane, what is the shift or delta value of your sample that is actually represented, and that is measured in parts per ppm unit, and that is denoted as a delta value. The chemical shift actually represented by delta. For proton, the range of delta is actually 0 to 10 ppm, and in case of 13C the range is 0 to 200 ppm. Now why TMS or tetramethylsilane is used as a reference sample or standard sample? The first one is it is soluble in most of the organic solvent. The second is it is very much inert, it is not reacting with your solvent or with your sample, and it has a 12 equivalent 1H and 4 equivalent 13C. 12 equivalent 1H, that means you see there is total 12 number of proton, 3 3 3 3. So that 12 number of proton actually generate very high intense peak. So that is easier or to observe the data, and is that TMS signal is set to 0 ppm. Compared to your TMS, your sample will be the difference between TMS and your sample actually given in the NMR data. And why it should not be reactive? Because if it is reactive, so obviously you will not get, or you cannot set it as a 0. So wherever you are using a reference, so it must not react with your sample or with your solvent. And for your information, when someone is doing NMR, so there is you may perform it in solution state or solid state. We will discuss solid state maybe in next week. In solution state, there must be some specific NMR solvent actually used. For example, CdCl3, that is chloroform CHCl3. Now that is deuterated chloroform. So almost all protons are deuterated, substituted by the deuterium. Okay. Now CdCl3. Then another one is the D2O, that is heavy water. Also DMSO6, that is dimethyl sulfoxide. There also you are substituting that hydrogen by the deuterium. So these are the most common NMR solvent actually used for solution state NMR. Now how it is scaling that delta value? So observed chemical shift in Hertz downfield from TMS, so that is difference between TMS and your sample, divided by the radio frequency, that is how much megahertz. So there is a specification. For example, someone is using 500 megahertz NMR, someone is using 300, or someone is using 900 megahertz. So if you divide it, so obviously now there is no confusion based on your machine. 1 minute. So that's why it is actually represented by ppm. And so if someone is doing in 500 megahertz and someone is doing at 300 megahertz, so the delta value for a specific proton will remain same. Now what actually we provide in NMR spectrum? What are the different information we provide? First is the number of signal, position of signal, intensity of signal, and spin splitting of the signal. We will discuss what is spin splitting. So basically 4 information we provide for a specific compound: the total number of signals we are getting, and the positions of signals, because obviously since all protons are not in the same electronic environment, so we will get peak at different position, and based on the number of proton the intensity will be different. And also there will be the another term, that is spin splitting, that is J value, that you also must represent. So this is uh, the structure of a NMR spectrometer. So these two powerful electromagnetic or superconducting magnetic, that is generating the external magnetic field, and here is the radio frequency input oscillator, and you put a sample. This is the test tube. So actually for NMR you have a specific NMR tube, and in that you provide your sample and you put here. Actually the height of the NMR is little bit high. So by stair you should put your sample on the top of the instrument, then you will get the data in this format. So only x-axis there will be the delta value or chemical shift. So this is the NMR tube basically, and also it is very much costly, around 500 600 per tube. And the NMR solvent those are used, I have already told, that is CdCl3, D2O, dimethyl DMSO, that is D3C2SO. And for 1H NMR you must first soluble your sample in a NMR solvent. For example, 6 to 10 mg is okay, and for 13C you need little bit higher, that is around 50 to 100 mg. So what you should do before preparing your sample, you first check the solubility of your sample in CHCl3 if you are using CDCl3. If your sample is soluble in water, then you should provide your NMR solvent as a D2O. If your sample is soluble in your methanol, then you go for the CD3OD. So then you go for the NMR solvent, because NMR solvent is also little bit higher cost. Now how you will get the data? So for example, if it is xylene, so you will get two different peak. Here is the EMS, that is reference sample, and the difference between your standard is actually represented here. You see all have the highest value 10 0 to 10, but in case of acid actually we used to get the delta value around 13 or 12.5 in that range. Now why there is 2 only? So here see, there is 4 aromatic proton and 6 aliphatic proton. Okay, now what we have learned or we have discussed about shielding and deshielding, from there you will get the idea. So if we compare the proton nucleus electronic environment, so see that CH3 is uh, less shielded, okay, and aromatic proton, because it is attached with carbon sp2, so this is more deshielded. That's why the more deshielded one will be at higher delta value. Okay, the shielded one will be lower delta value, the deshielded one will be higher delta value. Here is also that CH3 that is bonded with that carbon, and that carbon is bonded with chlorine. So obviously these are more shielded as compared to, sorry, these 2 proton is more shielded as compared to these 6 proton. Why? Because that CH2 is directly bonded with Cl, but this hydrogen, that CH3 and CH3, it is not directly bonded with the halogen. So since it is bonded with the carbon and that carbon is bonded Cl, so it is less shielded as compared to this proton. That's why these CH3 are coming at lower delta value as compared to this CH2. Now why intensity is different? Because these are the 6 proton and these are the 2 proton. You see, this is 2 proton and this is 6 proton. Okay, here is also, because of the same number of proton you are getting, the intensity is same. Now delta value is different. Now why delta value is different? It is because of the shielding and deshielding. Now one which is directly bonded with the oxygen, that is more deshielded, that's why it is coming here around 3.5. And since that proton, it is not bonded with other electronegative atom directly, it is coming at lower delta value. If you have any doubt here, please ask me, because this is the most important part. And from here actually you will you should know how you can generate a structure. So structure means, for example, if you are synthesizing some molecule and you are expecting that I have 7 different number of proton and it will come at that delta value. Now which proton will have a higher delta value and which proton have a lower delta value, it must be clear. So if you have any doubt here, please ask me. Nair sir, is it clear? You just memorize it, the which proton that is attached directly with more electronegative atom, that proton peak will come at a higher delta value. That is the basic. So whenever you are saying that, for example, if we compare, so since it is directly attached with oxygen, but here you see it is not directly attached with oxygen, because there is one another carbon. This carbon is bonded with this carbon, and that carbon is bonded with oxygen. But here the proton attached with the carbon that is directly bonded with this oxygen. So that's why this is more desilted, and that is coming at 3.5, and this CH3 is coming at 2. So there is also NMR chart where the standard delta value is actually given, and then by changing the electronic environment you will get the plus minus something, and you will get that idea. So this is the chart. So usually all alkyl group, if it is saturated, it will come within 1 to 2 delta ppm. If it is bonded with other electronegative functional group or oxygen or halogen, so usually halogen are coming around 3 to 4, or carbonyl or CsP2, those are coming 4 to 6, and all aromatic proton actually appeared more than 6. So from 6.5 it may go up to 8.5, and if it is aldehyde or carbonyl proton, that will appear around 10, and if it is acid, that will appear around 12 or 13. So now if you change that with different functional group, based on that you can get idea whether the delta value after modifying your sample will be coming at positive or right hand direction or left hand, downfield or upfield. So you just look into the electronic environment, how electronic environment is changing. If electron density is increasing, that means it is shielding the external magnetic field, so delta value will be lower. If it is electron density is somehow reducing, so it is experiencing more magnetic field, so it will come at higher delta value. Yes, yes. Sir, actually for proton it is 0 to 10, but we actually provide proton NMR data 0 to 13. Sir, you may use 300 megahertz, you may use 500 megahertz. It will not change, because you see here I have shown you that we are representing delta, the difference between the sample and your TMS divided by the frequency of your NMR spectrometer. So whether it is 300 megahertz or 500 megahertz, the delta value will not change, because now it is per unit megahertz, na? So if someone is doing, for example, in 300 megahertz, the same sample I am running at 500 megahertz, I will get the delta value for a specific proton at the same position. Yes, yes. So that's why they use that delta value. They need that delta value, so that there will be no confusion. Otherwise, it will create some problem, na, confusion. The same material will show at different position. And see, that's why it is in ppm actually. The delta unit of this chemical shift is represented as a in ppm. Now what I have just informed you that why we represent it in NMR. First is the position, the intensity, and one thing is the spin coupling. Now what is spin coupling? So here we will show you later. Here you are getting a single peak, right? For a specific type of proton, for example this CH3, you are getting a single peak. Now sometimes you will see the single peak is splitted in two different at the same position, but it will not as a single line, it will be two line. So that is called the doublet. It may also split in three, that is called the triplet. So that is happened because of the spin-spin coupling. So what is that? Now the coupling of the intrinsic angular momentum of different particles. So obviously, as we know, there is a spinning and also it is rotating. So there must be a angular momentum. Now such coupling, what is the reason? Now two nucleus which are spinning, they if air goes very much, that will interact with one another. And when it is interacting, so there will be a change in the magnetic field, experiencing magnetic field. So that's why it is very much important such coupling between pairs of nuclear spin in NMR spectroscopy, as it can provide detailed information about the structure and also geometrical conformation of the molecules. Now, spin-spin coupling between nuclear spin and electron spin is responsible for the hyperfine atomic structure. Now, what is the result behind that? Now, if an atom is under examination or that is perturbed or influenced by a nearby nuclear spin, the observed nuclear response to such influences and its response is manifested in its resonance signal. So, if a spinning nucleus is influencing by another spinning nucleus that is nearby, so it will uh, manifest that how much it is interacting in the response signal. Now, this spin coupling is transmitted through the connecting bond. So, it is only possible if it is directly bonded with the atom. We will discuss in, we will give you example. And it function in both direction. Thus, when the perturbing nucleus becomes the observed nucleus, it also exhibits signal splitting with the same J value. So, spin-spin coupling actually represented by J. Now, for spin coupling to be observed, the sets of interacting nuclei must be bonded in relatively close proximity. So, either it is vicinal or geminal location. So, either with the same atom or just one atom later, and oriented in a certain optimal or rigid configuration. So, here also called the indirect spin-spin coupling sometimes, that is coupling between the two nuclear spin due to the influence of the bonding electron on the magnetic field running between the two nuclei. And J coupling provides information about the conformation, the hydron angle, which is estimated using the Karplus equation, and it is important observable effect in 1D NMR spectroscopy. There is also another 2D NMR, and the coupling constant actually, you whenever you are providing NMR data, you should also provide the value of the J constant or coupling constant, and it is represented or given in frequency unit, that is Hertz. And what is this? It is basically the measure of interaction between the two spinning nuclei. Now, how it is represented? For example, let's take this example. So, this is 3 carbon it is showing, and this is HA, this is HB, this is HC. So, here 2 HC. Now, if you do the NMR study of this sample, what you will get? First, that HA, it will not a single line, it will be 2 line. If you zoom the spectra, you will get the same intense 2 line. Why it is happens? That is because of the coupling with the HB. Since HA and HB are close by, it will influence each other. That's why we will get doublet type of peak. Now, in case of HB, since it is interacting with both HC and HA, and also sometimes it may influenced with these HC also, you will get this type of peak. So, this is a single proton, but because of this very small influence, you will get this much of hyperfine structure. So, that's why NMR is very much, it can precisely determine the structure or the geometry of the molecule. and you see the Hc, these two, now these two are the equivalent proton. Now that's why it is higher intensity, but since it is interacting with the Hb, you are getting doublet type of peak. So ideally it must be a single peak, but since there is a coupling with this Hb, you are getting two peak. Now the question is, it also depends that hyperfine structure, it may not be possible to observe with low megahertz NMR. For example, it is 60 megahertz, you may not get that hyperfine structure. If it is higher, for example 500 or 600, you will get that hyperfine structure. That means higher will be the radio frequency strength, frequency, you will can probe much deeper, or you can get very deep or very fine information of the structure, whether there are some interaction or not. Now sir, is it clear the coupling, or why you are getting this doublet or triplet or singlet? Or if anyone has any doubt, please ask. Hello, is it clear na? Okay. And from NMR you can also check the tacticity. So based on this, if some polymer has isotactic or same polymer with a syndotactic attractive, you see there will be the difference in the NMR spectra. For example, in isotactic you are getting a peak around 2, but you see in case of atactic or syndotactic there is no peak around delta value equal to 2 or 2.2. So that much precision is possible in NMR. Now sensitivity, so we have discussed now 1H or proton NMR. So there are others also, that is 13C, 31P or 29Si. Now the sensitivity of NMR signal depends on these four parameters. So first is the magnetic field. So what we have already discussed, that higher will be the magnetic field, the sensitivity will be higher. Next is the temperature. Now the temperature, how it can influence? First of all, the spin-spin coupling, or there are another two term that is called the spin lattice relaxation or spin-spin relaxation. Those are also dependent on the temperature. And another thing, that is the Boltzmann distribution. So higher will be the temperature, then you will get lower sensitivity, because you see the population density will be higher if the temperature is higher, but we need the ground state population must be higher as compared to your excited state. So that's why higher will be the temperature, the sensitivity will be low. The third thing is the gyromagnetic ratio, and that is related with the sensitivity with in 3 cube order. So that is depends on the element to element. And the last one that is very much important, that is the abundance. How much naturally it is abundant. Higher will be the abundance, higher will be the sensitivity. Why? Higher abundance means the how much naturally occurring element is magnetically active. So in case of 1H, it is 99.985%, those are NMR active. But 13C, that is very small amount, that is 1.1%, that is NMR active. And this is the magnetic field, that how much magnetic field, it is gamma by 10%. 1H is 26.75, 13C is little bit less, it is 6.73, 31P is comparatively good, 10.84, and the radio frequency, that is 500 megahertz, so it little bit higher in case of 1H. And for 13C you need 125.8, and for 31 phosphorus you need 202.6, and in case of 29 SI, that is 99.5. So most common is 1H and 13C, but people also sometimes you need 31P for some specific uh, purpose, or for example if somebody is using some flame retardant uh, material in a polymer matrix, for that you maybe you need to do the 31P NMR. Now we should discuss little bit about 13C. Now what is the advantage of 13C? Why you should go for the 13C NMR? First of all, we have discussed that for 1H we usually cover delta value from 0 to 13, but in case of 13C you can go from 0 to 200. So obviously if the number of different carbon is higher, still they will be clearly visible in case of 13C. But if, for example, if some sample has very high number of different proton, so within that small scale, so there will be a chance of merge with one another. So that is one disadvantage. But in case of 13C, because of higher scale, they are can well separated from one another. And also, so it is 20 times higher or more resolved than the 1H. So the chance of overlapping in case of 1H is very high as compared to your 13C. And the next thing is the spins coupling of the 13C. So if you take this example 2-butanol, so that 3 proton will be interacting or spin coupled with just CH2. It may also interact with that OH also. So it will be little bit complex, but you can obviously differentiate it from 1H also. Now 13C 1H spin coupling makes the NMR interpretation difficult due to the overlapping peak. So that carbon and that proton that will overlap because they are active, because all proton are NMR active. Now if this carbon is 12 or this is 13, because you do not know which one is 13 or which one is 12, those are the 13, they will only react or active in the NMR. So these are the problem in case of 13C, because it the 13C 1H spin couplings can takes place, and it will uh, make you hard to differentiate or to analyze the data. For that, what you should do, you should go for the decoupling. What is decoupling? So to get the unwanted 13C 1H coupling to be eliminated from 13C NMR, or to simplify the spectrum by using decoupling technique. Okay. Now for that, what you should do, you should provide a simultaneous secondary radio frequency and 90-degree angle towards the external field direction, magnetic field direction. So that radio frequency has a very broad frequency range, including all carbon and hydrogen excitation. There is proton resonance at 300 MHz and carbon resonance as 75 MHz. Here the saturation of H hydrogen occurs, and the rapid transition of the hydrogen between alpha and beta, which lead to time average view between the two states. Hence, they do not spend sufficient time in specific arrangement to couple with the latency nucleus. So, with the radio frequency that is already there, you should provide another secondary RF, so that all hydrogen can excited, so it will not get sufficient time to interact with the carbon. That is basically here the mechanism is actually going on here to decouple the 13C 1H coupling. Okay. So by providing another external radio frequency, the saturation of hydrogen can occur. So it will, the alpha and beta, it will transit from alpha and beta. So it will not get the sufficient time to interact with your 13 carbon nucleus. So after decoupling, you will get these 4 different carbon, A, B, C, D. You will get 4 different. Before that, because of that spin coupling, the with 13C and 1H, you may get triplet. Sometimes you are getting quadrate, but after decouple, you will get a very single peak with 4 different carbon. Now, still now we have discussed about the solution state. So sometimes if your sample or more specifically rubbery type of material, those are very much less soluble in any solvent, you should go for the solid state NMR. Now in case of solid state, the uh, result is you can clearly see that when in solution you are getting very sharp peak, but in case of solid state you are getting a very broad type of peak. So this is a single peak. This is also a single peak. Now why it is that? Because we know that in solid state, because there are very uh, large number of molecules are bonded very tightly, so they can interact with the neighboring nucleus. That's why you are getting a very broad peak, and that is actually solid state used for powders or single crystal or any amorphous material, and also in biological application for analyzing different tissues. You should go for the solid state NMR. Now there are the 3 important term that is used in solid state. First is the isotopic value. So what is isotopic value? So if this is a single peak, this total is a single peak. Now the center of gravity is the average value of the principal component is called the isotopic value. So if you may say this is the delta ISO value, and the omega, that is the span describe maximum means. What is omega? Omega is from here to here. So a peak area from here to here, it is the span or maximum width of a peak, that is represented as a omega. And the skew of the tensor is a measure of amount and orientation of the asymmetry of the tensor depending on the position of delta 11, delta sorry, position of the delta 22 with respect to delta ISO. So this is delta 22. So the position with respect to delta ISO, how it is orienting, that measurement is done by the kappa value or skew of the tensor. Now principal components delta 11 greater than delta 22 greater than equal to delta 33, and isotopic value is average of delta 11, delta 22 and delta 33. But it is little bit difficult to analyze the solid state NMR because of this high Broaden peak, and you need dipolar coupling. This is the interaction of one nuclear spin, what we used to say spin-spin coupling. Now this is the dipolar coupling. So this is interaction of one nuclear spin with a magnetic field generated by the another nuclear spin or vice versa, and this is orientation dependent. So now what is the difference between JJ coupling and for spin-spin coupling and dipolar coupling? So what we have said that for spin-spin coupling, it must be bonded with the atom, but here you don't need direct bonded atom. So if it is nearby, it can also interact. So here what we show you, you see that must be directly bonded with that carbon, then only it will influence. If it is not bonded, it will not influence. So that is the difference between the JJ coupling and here dipolar coupling, and this is direct through the space orientation, which is independent upon the gamma of each nucleus as well as RJK. This is represented by this equation. And another term is the Zeeman interaction. So it is the interaction between the magnetic moment of the nucleus and the external applied magnetic field. It is actually in the order of 10 to the power 8. And the nuclear magnetic moment ampere meter square is proportional to the nuclear spin quantum number, that is I, and the gyromagnetic ratio, that is mu equal to theta I into h by 2 pi. Thus the Zeeman interaction occurs only with the nuclei which possesses a spin greater than 0 and yields 2i plus 1 energy levels of separation. Since the Zeeman interaction incorporates the magnetostatic ratio, a constant for each particular nucleus, so the frequency of each nucleus is different at a specific applied magnetic field. So obviously, since gyromagnetic ratio is a inherent property, and now Zeeman interaction is dependent on this, so the frequency of particular nucleus is different at a specific applied magnetic field from other. Now, what is the application of NMR? If we say what is the application area in case of polymer, if uh, or other elastomers or composites. Now, first of all, the traditional method, vapor pressure or membrane osmometry, light scattering photometry. So, to determine the molecular weight, there are different uh, technique. So, we know that cryoscopic techniques are actually used to determine the molecular weight of a polymer. Now, if someone wanted to know from NMR what is the molecular weight, so three conditions that must the material should satisfy. The peak area of the intensity due to the same proton at a specific delta value should be additive. Additive means it will be the total delta value should be delta 1 plus delta 2 plus delta 3 for a same proton. The second condition is overlapping of proton in different groups should be absent. And third one is resolutions of proton or different segment of a copolymer should be similar. Now, actually, it is very difficult to measure the molecular weight because we know that polymer molecular weight is more than 10 to the power 5 or 10 to the power 4 order. But for that, to get molecular weight from NMR, the condition is the number average molecular weight should be less than 20,000. So, in practically, it is difficult to get the molecular weight from NMR if the polymer has a very high molecular weight. Now, how actually it calculate? So, here is the example. So, there is N group R. Here R is the uh, dinitro or 3,4 dinitro benzene with COCl. So, after introducing a group with known number of proton, so now you know that there are three different proton. One is here, and another one is here. Okay. So, total there are 6. The intensity of various proton in the monomer unit of the polymer at different chemical shift is compared with that of the known proton. So, with compared to these 3 proton, you are measuring the proton of the repeating unit. So, dp plus 1, the equation is dp plus 1 equal to ICH3 by 6 divided by I aromatic by 6. What is ICH3? This CH3 CH3. And what is I aromatic? This 3 carbon, this 3 proton. So, here I indicates the intensity at the particular chemical shift of the respective proton. So, this is the equation. So, you will get a specific delta value for this proton, it is alkyl proton, that is present in repeating unit, and you will get delta value at aromatic region for this proton. So, since total number of proton is 6 and here is it is also 6, so divided by 6 you will get the data. You can also measure the Tg. So, first is the molecular weight, second is the Tg. How you can analyze or how you can check the Tg? So, it is actually depend on the two uh, phenomena, that is spin relaxation and spin lattice relaxation. So, one is termed as T2, that is spin relaxation, and another one is the spin lattice relaxation, that is T1. Now T1, the relaxation time in a rotating frame, now polymer motion. So we know what is Tg, above which the segmental motion is start. Now above the Tg that occur in the megahertz or kilohertz regime, so T1, T2 will change. So T2 is the T2I. Now T2I, here it is the equation that is actually required to measure. Mt is Ma0 exponential minus T by T2A plus Mb0 exponential minus T by T2B to the power alpha plus Mc0 exponential minus T by T2C. Now what is T2I? It is T2 of the ith relaxation component. So T2 is the spin relaxation time, and T1 is the spin lattice, and Mi0 is the amplitude of the same component which suitably normalized represent the percentage of proton nuclei associated with the T2. Alpha is the shape parameter of the wave Boolean component. So T2A and T2C and alpha at their base fitting value 70 microsecond, 10 millisecond and 1.5 respectively. So this is just by doing the NMR spectroscopy at different temperature. So here it is more understandable that by doing the NMR test from a very low temperature, you are plotting spin relaxation time T2 versus temperature. Below a certain temperature, T2 is almost constant or decreases very slowly, and after a certain point, T2 increases more rapidly. Now at Tg, the mobility of protons that is connected with the carbon atoms in the pendant group, that is the segment that increases dramatically with temperature indicated by a stiffer, or the slope of this graph is higher. They are indicated a stiffer slope on the T2 temperatures curve. So in that way, you can measure the Tg of your material. So we have discussed today about the NMR spectroscopy. We have discussed little bit about 13C. So next week we will discuss about solid state little bit and also 2D NMR. And here I have set few questions. So is it clear to all whatever we have discussed today? What are the basic condition or criteria required to be NMR active? And then what is spin coupling, or what is delta, shielding, deshielding? Okay. So first question is 1H and 13C are the two of the most common nuclides studied by high field NMR spectroscopy due to their abundance in human tissue. Other isotopes that have been studied include 14N, 17 oxygen, 31P, 79 bromine and iodine 127. Based on the information, which of the following nuclides will not be considered suitable for use with the NMR spectroscopy? So what is the criteria of to be NMR active? Odd number of, okay. So based on that, what will be the right answer? So which one will not be considered suitable? That means which one will be inactive? The question is, among these following nuclides, which will not be considered suitable for use with NMR? So which one has the even number of? So obviously the neon with 20, so that is because of the even number of proton or neutron, it will not be suitable for a NMR activity. So answer will be the C. Now deuterated solvent in NMR sample is used to stabilize the magnetic field, obtain good field homogeneity across the sample, set the uniform radio frequency, or all of the above. Why you should go for the deuterated solvent to check the NMR of your sample? So I have already discussed that either CD3OD, that is deuterated methanol, or deuterated H2O, or deuterated chloroform you need for as solvent for solution NMR. Now, why? Please answer anybody. Why? No, no, no. It should not be have different magnetic moment. Na? That's why we use. Because that's why deuterium. Na? If it is proton, so it will also show its own NMR spectra. So that's why you should go for deuterated. So it will stabilize the magnetic field. But still, for for every NMR solvent, you will get specific peak. For example, if you are using CDCl3, you will get a very sharp peak around 7 point. Okay. If you are using DMSO D6, you will get a very sharp peak around 2.5. Now, why? The thing is, whenever you are using deuterated substitution, it is not possible to substitute 100%. When you are substituting proton of chloroform, that is CHCl3, you are substituting H by D. So it is not possible to substitute 100% H with the deuterium. So that's why there must be at least 0.01% or 0.001% CH3L3, and that is why you will get very sharp peak for different solvent at different delta value. Okay. Assume that a proton is scalar coupled to proton with a different chemical environment. If this proton shows a triplet signal, how many proton is in scalar coupled to? So if you are getting 3, that means triplet. So we have discussed the spin coupling. So if there is you are getting a triplet, then how many protons in scalar coupled to? So for how many different proton actually coupled with that specific proton? Yes. If there is 2, so it will be 2 plus 1, 3. If it is 3, then you will get quartet type of splitting. Okay. So thank you for your presence and for your question. So still, if you have any doubt, ask me. Otherwise, I'll stop here and we'll discuss next week. First, we'll discuss about 2D NMR and solid state NMR little bit, and then other things. Nair sir, everything is clear now? Okay. 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 So now I am stopping. Yes. Yes. You are asking something? No, actually, 1 minute.